Now in class 12th, I am taking the magnetic permeability. So let's according to Bio-Savart's law, the magnetic field due to current element is given as dB equal to a constant K I dl sin theta upon r square. Now you can see from here that this if I take this B is equal to, this is now your K integration I dl sin theta upon r square. K is a constant where K equal to constant. Its value is 10 raised to the power minus 7 Weber per ampere meter. This is in M case. And this K is equal to 1 in CGS or Gaussian system. So this is the constant, and this constant depends upon the medium upon the system of units, medium and the material of the conductor. So here we are taking only to this K to be a constant one, like this. This is in MKS value and this is in CGS, the value of K is equal to 1. Now we have to find the variation of this B with this I, dl, sin theta and r square. So from here you can see the variation of this one, that is B. Now this, if we take this dV is proportional to I. So now we are having a curve like this. This is, suppose we take this dV, this I take now I, then this will be a straight line. dV proportional to I. This is now your second. And now second we are having, so this one is that this dV is proportional to what? dl. So now we are having the curve like this. This is now dV. This is now your dl, then again we are having a straight line. So this dV is proportional to dl. And now we have another graph showing this variation, that this dV is proportional to sin theta. What does it mean? That if we are having this angle theta on this side 0 and here we take this dV, then this will be the graph like this. Here this B is maximum, here this for pi by 2 and this is for pi. And now put to this one, that we have this dV proportional to 1 upon r square. So we are having a curve like this. This is suppose now we take this R, this is now here we are having this dV, then you will have a curve like this. So this dV proportional to 1 upon R square. So these are the some of the graphs that give you the variation of the magnetic field due to the current element and the distance, the angle, and that we are having the length of the element and the current flowing through the conductor. Now we are coming to this constant K. Constant K. This is equal to mu naught upon 4 pi. And its numerical value is equal to 10 raised to the power minus 7 Weber per ampere meter. This mu naught, this is called the magnetic permeability. This we also see that this mu naught is the absolute magnetic permeability. Where mu naught absolute magnetic permeability. Then the question arises that what is the meaning of permeability? What is the physical meaning and how does it stand with the different factors? Are there some factors that affect this absolute permeability, the magnetic permeability? So, the magnetic permeability is the measure of magnetization of the material in presence of magnetic field. मैग्नेटिक फील्ड तो क्या है कि जब हम किसी मटेरियल को मैग्नेटिक फील्ड के अंदर रखते हैं तो भाई वो कितना मैग्नेटाइजेशन किया जा सकता है उसका, वो कितनी मैग्नेटिक प्रॉपर्टीज असेंबल कर सकता है, तो जितनी मैग्नेटिक प्रॉपर्टी वो गेन कर सकता है दैट इज कॉल्ड द मैग्नेटिक परमीबिलिटी। तो मैग्नेटिक फील्ड लाइंस होती हैं, तो मैग्नेटिक फील्ड लाइंस से जो वो उस मटेरियल के अंदर कितनी एक्सटेंट तक जा सकती हैं दैट इज द मैग्नेटिक परमीबिलिटी। Denoted by Greek letter mu. So this if we are having to this one units of mu. Now this I have told you this Weber per ampere meter. This is now one unit. Second unit is Newton per ampere square, and third unit is Henry per meter. Henry per meter. Henry per meter. H for Henry. Henry per meter. Henry per meter. And that it can have, these are the units in MKS. In MKS. In series its value is equal to 1, so we are not concerned with that one. Also, now if we take the ratio of magnetic field to magnetic field B to magnetizing field, H is called the magnetic permeability. So now what we have? This mu is equal to B upon H, or this B equal to mu H. So if we write down in terms of vector, then we can write it like this one. So this is for material or for medium. And this is equal to B naught equal to mu naught H. This is for free space or vacuum or air. So if we write down for free space or for vacuum or for air, then we have this mu naught equal to this B naught equal to mu naught into H. So mu naught is also called the constant of proportionality between B and H. So mu is also called the constant of between magnetic field and magnetizing field. B and H. This is also a constant of proportionality, or simply a constant. The magnetic permeability. is also defined as magnetic flux per unit magnetic pole strength. So what we have, this mu naught upon 4 pi is equal to magnetic flux upon magnetic pole strength. How do we arrive to this one? Because I have told you that this is what the Weber per ampere meter. Weber, that is the magnetic flux, and this is this ampere per meter. This is the magnetic pole. So magnetic permeability is also defined as the magnetic flux per unit magnetic pole strength of the material in presence of the magnetic field. So this is one more relation. So this is for what? That we are having this for in the free space. But for a material, now we can have this mu or mu naught. They are not the dimensionless, but they are having the dimensions. So dimensional formula of mu. So what we have? We are having the unit is Newton per ampere square. This is now smallest unit in the case of this one. So we can have this mu equal to m1 and this is now your L1 t minus 2 and a minus 2. This is the dimensional formula. The relative permeability, this is the one more term associated with this this magnetic permeability. The ratio of magnetic permeability of material to the absolute magnetic permeability is called relative magnetic permeability. Denoted by mu1. This is also like this, so we can have or this mu r is equal to mu upon mu naught. This is what we mean. The ratio of magnetic permeability of the material to the absolute magnetic permeability. Mu upon mu naught. Now this mu r is dimensionless quantity because it is the pure ratio. Dimensions of mu r. So this is what? N0, L0, T0. So this is dimensionless. Dimensionless. It has no unit at all, but it has a very significant role when we select the material. And we can have one more definition that we can derive from this one is that this mu r is equal to magnetic flux in material upon magnetic flux in free space. In free space. This is one more by having the similar this definition. And this we can have for dimagnetic material. This mu r is less than 1, and for paramagnetic material this mu r is greater than 1, and for ferromagnetic material this mu r is very greater than 1. So these are having a very important role while we are having the material in the magnetic field. So this is our general experience that the ferromagnetic material acquire maximum magnetization when they are placed even in a very weak magnetic field. Now we are talking about the magnetizing field H. Magnetizing field H denoted by this one. So the unit of this one unit is your ampere per meter. This is in MKS, and we are having this orostate in CGS. So what we have that this 1 ampere per meter is equal to 4 pi into 10 raised to the power minus 3 orostate. This is a very important relation because sometimes the question is given in case of this orostate, then you can convert it into the ampere per meter because all the units will be given in the MKS. So if someone is given in CS, then you have to convert that into the MKS units. So this 1 ampere meter is equal to 4 pi into 10 raised to the power minus 3 orostate. Now we'll see that what factors affect the magnetic permeability. Factors affecting magnetic permeability. So now first is the material of conductor. Second, the position of conductor in magnetic field. Here by position you must understand that whether this conductor is nearest to the magnetic field or just away from the magnetic field, then definitely the distance will have a very important role while getting the magnetization of the material. Second, the humidity. Fourth, the medium around the conductor. Fifth, the temperature. You see that when the temperature is raised, the magnetic properties of the material change. So temperature have a very important role in the magnetization of the material. And sixth, the frequency of applied magnetic field. Applied magnetic field, because the applied magnetic field may have the frequency, it may be the variable one. So when there is a current that is varying with the time, then definitely this magnetic field will be varying with the time. So we will have the frequency of this one. So these factors will affect the magnetic permeability. So these are the 6 factors. First, the material of the conductor. Second, the position of the conductor in the magnetic field. And third one is the humidity. And fourth is the medium around the conductor, the temperature, and the frequency of the applied magnetic field. And you can also see a variation of this mu with by means of a graph. So that I will have this one. If suppose we are having this guy, I have this B, this is now H, this is now 0, this is now your x-axis, this is now your y-axis. So now then this you draw the line, then this is for mu naught, this straight line shows for mu naught. That means what for the free space, magnetic permeability of the free space. If we have, you can have this, it is for dimagnetic. Mu for dimagnetic. If we are having the graph like this, a straight line, that is mu for paramagnetic. And if we are having this graph like this one, then this is mu for ferromagnetic. Ferromagnetic. So this graph is for ferromagnetic, this graph for paramagnetic, this is for mu, the free space. Mu naught for free space. This is mu for dimagnetic. So just by having a graph between P and H and you are given these lines, then you can find that which is for free space, which is for dimagnetic, which is for paramagnetic. So if suppose one of them, the lowest one, that will be the dimagnetic. Just below or just above to this one, this is now for free space. Just above to this one, this is now paramagnetic. Just above to this one, this is now ferromagnetic. In case of ferromagnetic, we are getting a curve like this. This is going and then it takes the turn. So this shows the value of mu for different materials. I think that this will give you a good idea about this magnetic permeability. So thank you very much.